Hello everyone, my name is Filip Benna. I work at Codasip as a product manager, and as it was already introduced, I will talk about processor customization today, especially about how to do processor customization responsibly, taking the verification of the processor into mind. Just a quick overview of what my talk will be about today. So I will first introduce the company because I assume that not everyone knows Codasip. I will explain why should you care about processor customization. Then I will talk about the way Codasip approaches processor customization in the way we believe is very responsible. And I will also use this opportunity to introduce some of the new products we have recently announced. So Codasip offers quite unique combination of a processor EDA tool, which helps you to automate processor design as well as processor customization, and a portfolio of RISC-V processor IP. We have started before RISC-V was a thing, but at the same time we believe we introduced the first commercial RISC-V processor to the market. And since RISC-V became very popular, we moved all of our processor IP into this architecture. We are mainly based in Europe, where all of our engineering is, but we have sales presence all around the world. As you probably already seen in the subtitle of my presentation, processor customization is like the vital thing to Codasip. You can see that it's actually part of our vision. We call processor customization done using our methodology custom compute, and I will use custom compute as like a silver lining throughout the entire talk. The power that the title of the presentation uses is obviously the custom processor. We believe that processor customization is actually a natural progression. You can see that the differentiation in products started with custom software, then it moved into custom SoCs. And we believe that the next step, the step that is actually already happening, is the customization of the processor core. So the customization is progressing deeper into the end product. The existence of architectures such as RISC-V are actually validating the fact that there is an interest in processor customization. The diagram that you can see behind me is showing the two basic principles how RISC-V enables you to do processor customization. The orange line is representing what the standard RISC-V instruction set extensions enable you to do, which is add into your processor a new instructions which are targeting a common segment of applications. These extensions are still relatively generic, so using this simplified graph, essentially the trade-off between the area of the processor with the custom instructions or with the standard instructions and extensions, and the performance or other benefits that you will get from adding them is quite linear. However, the second way you can customize a RISC-V processor is what the purple lines show, and that's adding a completely custom instruction, something that's very specific to your application. And as you can see, the benefits that you will get from doing so are much bigger because you are finding the instructions which are tailored exactly for your use case. There are other reasons why processor customization is important. Different trends in the industry, like Moore's Law, which I'm sure that many speakers repeated during the day, is actually slowing down, and companies are finding another ways how to make sure that their products are advancing, how to make sure that they are differentiated. So processor customization is one of the ways to achieve that. So that I don't speak only theoretically, I want to show you a couple of examples what customizing a processor core may deliver. On the slide behind me, you can see a couple of very common applications that we see our customers using. And you can see, I will show you over the time two different metrics. The first one that you can see is performance density. So that's the performance over the area of the processor. And you can see that performance density for two types of processor. The gray part is a standard RISC-V processor using only the standard RISC-V extensions, whereas the purple one is what you can get if you start using completely custom instructions. And you can see that the benefits in the performance density are really big. They go from 2x for something like the SHA-512, but they can go much higher, for example, for the CORDIC instructions. Using custom instructions usually means that you also execute the same task with less instructions. That has other benefits as well. You save a lot of power. You save a lot of power because you're using less instructions, but also because your processor can do the same task faster and can stay longer time in low power modes. So you can see that you not only get performance benefits for small area increase, but you also get big power savings if you start using custom instructions in your processor. I believe we are not the only ones who have noticed this. Behind me you can see a couple of quotes that I found online or I noticed when I was attending different conferences. But different industry media are talking about processor customization. Hyperscalers are using this during their keynotes, different conferences and industry events. We see a lot of emerging competition trying to focus on exactly the same thing. So it's definitely not only us who believe that processor customization is the future. However, what does it take to actually deploy a custom processor, right? So far I was only talking about what the title of this talk considers the power, but how about the responsibility that you need to take if you decide to deploy a custom processor? I will talk about a couple of challenges that we see throughout the experience that we have gained in the last 10 years selling processor customization, and how does Codasip approach them to actually help our customers. The first one is that when I talk about processor customization, most of people think that I talk about changing the RTL implementation of the processor core. That obviously is an essential part of that process, but that's not the only one. If you customize an instruction set of a processor, you need to modify all the software toolchain as well. Otherwise, you will not be able to program the processor core using the standard mechanisms that you used to, like compiling the C code. Modifying the tools is, however, requiring a completely different skill set than modifying the RTL. It's commonly done by different teams. Also between the individual software tools, like let's say C compiler and simulation model, you will see completely different type of experience and skill set required. But if you think about it, all of these people actually transfer the same type of information into a different technology, right? You want new instruction in your processor, so your design team will have to transfer this into the RTL implementation, but your compiler team will have to transfer the same type of information into a compiler framework. So there is a lot of overlap, even though they are doing quite isolated tasks. The way Codasip is approaching it is by designing our own processor description language called Codal, and a tool called Codasip Studio, which is processing that language. In this language, you can describe both the processor's architecture as well as its microarchitecture in one processor model, and then Studio will automatically generate for you both the RTL implementation of the processor as well as all of these software tools. It doesn't mean that you will need only one person implementing the custom processor. Of course not. You still need to understand the processor architecture to some extent, but you can concentrate this effort into one model, which is saving a lot of duplication that would otherwise be happening. Another thing we do to enable easier processor customization is we're not asking our customers to start from scratch. Obviously, you probably know where the differentiating factor in your processor can be, but it doesn't mean that the entire processor has to be written from scratch. Large parts of the processor will probably be pretty standard. And so we offer also a portfolio of existing RISC-V IP, as I mentioned, which ranges from simple microcontrollers all the way to multi-core application processors that you can use as a baseline for your custom processor. At the same time, we provide also some specific functionality like certified processors for functional safety or different memory safety features that our customers are interested in. Another challenge I would like to mention is represented by this graph. It's maybe a little bit cryptic, but I will very soon explain what it means. The trend of building different processor architectures that we can see now with a lot of new markets emerging is not completely new. In the past, most of the processor companies were all maintaining their own processor architectures. And in that times, there was a lot of people working on processor design, on implementation of different software tools that I mentioned, such as the compiler, etc. However, over time, many of these architectures have essentially disappeared. The whole market of processor architecture has consolidated, so the talent kind of disappeared from the market. So now, when there is a new push to create differentiated processor architectures, the talent is really rare. So finding a processor architect or a compiler engineer may be a pretty difficult task. Another part of this challenge is what I would call hidden effort. I was deliberately not mentioning one of the really important parts of the processor design, which is verification. And that's because this is actually something that a lot of people considering to design processor don't take into account. The verification of a processor is also a very rare skill. It's very difficult to find people who know how to do it. And at the same time, it may take up to 70% of the entire design project. So that's another big problem. Especially in the RISC-V market, we're noticing issues with the quality of existing RISC-V IP, and we believe that that may be one of the issues, that finding the people who can actually do proper processor verification is very difficult. It would be quite irresponsible from us to talk about the benefits that processor customization will deliver and kind of ignore everything that I just said, right? So the way that we approach this is that we created segmentation into something that we call levels of customization. What you can think about when I mention levels of customization is actually a productized way how we can use our products and technology to achieve a different trade-off between the level or the degree of how you can customize a processor and the impact it will have on the design and the verification that you as our potential customer may need to take on. This diagram starts with the gray dot. That represents the standard off-the-shelf IP market, where you get essentially no freedom to customize the processor. Obviously, you at the same time don't need to invest any design or verification effort into getting such processor. As you can see, all the other levels that I have on my diagram provide more customization freedom. And the last two obviously require also some design and verification expertise to be available in your teams. In the next slides, I will talk mainly about the levels that we call configurator and bounded customization. For customers who cannot invest any design or verification effort into building their custom processor, we provide an extensive configurability of our existing processor cores. So the only thing they have to do, and you can see it on the screenshot from Codasip Studio that I have on my slide, is go through the set of these configuration options where they can choose from existing RISC-V extensions, which may be the standard ratified instruction set extensions, or maybe our own instruction set extensions that we have designed for our customers, such as the DSP functions that you can see on the slide. You essentially only check the boxes that you like, and then using a lot of these play buttons that you can see on the left-hand side in Studio, you can generate all of these outputs automatically, and all of them will represent the configuration that you have chosen. So if you click on, let's say, simulation model, you will get a simulation model implementing exactly the configuration that you have chosen. This sounds really easy. It's very nice to put it on slide, and it kind of sounds natural, right? If RISC-V comes with this configurability, why wouldn't you offer it? But I would challenge this a little bit. Claiming that there is a lot of configurability that you can put into your processor IP is something that should be backed by explaining that it actually took a lot of effort to achieve this, right? So that we can allow our customers to choose from thousands of different configurations of our processor IP. on their side, build it on their side, use it, and know that they can go into tape-out with such configuration. We needed to build really strong and experienced verification team. We needed to acquire a lot of computational resource, a lot of licenses, and a very clever verification strategy which allows us to bring this entire configuration space of our processors to tape-out quality. So how about, or what if, you need a truly custom instruction? Something that we couldn't think of, so we never included it in our configuration space because it's very specific to your software application. This is exactly why we have the second level, bounded customization, where you can add a completely new instruction into an existing Codasip processor based on your very unique needs. In a standard design flows, this would require the re-verification of the entire processor core, because if you modify the pipeline to include a completely new instruction, you can essentially throw all the verification that was done away. However, that would be a big problem based on what I mentioned a couple slides earlier, that the verification resources and skills are very scarce, so you might not have them. This is why we created a very clever verification strategy which allows them to insert new instructions into our processors. These instructions have to comply with a set of rules, but once they do, you don't need to re-verify the processor again. The only thing which needs to be verified is the functionality of the new instructions, because we believe that you want to be sure that they are working. This mechanism can be used for a lot of common customizations which differ in implementation, so each of our customers may want to have it implemented in a slightly different way. You probably remember a lot of these from the diagrams that I was showing in the beginning, where I was showing the benefits of processor customization. Adding new instruction into an existing pipeline is not just a verification task, right? You have to be able to design such instructions so that it works correctly in the pipeline. And if the original pipeline of the processor was not designed by you, it can become pretty tedious, because you might not be sure which parts of the low-level logic you can touch, which parts of that you can modify, and what will be the consequences of doing so. Luckily, the abstraction that we have in our Coda language allows us to concentrate the definition of these new instructions into a very simple and quite isolated blocks of code, as you can see on this slide. The block of code is essentially representing what does the instruction semantically do. It looks almost like a normal C code, but then when you compile the codal model in Studio, Studio will insert the functionality into the processor pipeline, modify the low-level logic so that it now works with your custom instruction as well, without you needing to understand how does the pipeline work. The same description, by the way, is used also to generate the software toolchain. So you will get the software toolchain generated from exactly the same description. As I have mentioned 2 slides ago, you still want to verify your new instructions. You still want to make sure that they are doing the thing that you would like them to do. We knew that this needs to be as easy as possible as well, so we created a top-level verification framework that can compare your new customized processor RTL with a reference model and their complete architectural state after every instruction that you execute on them. Big part of this verification methodology is also supported through the capability of Codasip Studio to generate what you will need to execute this framework. So Codasip Studio can obviously generate the customized RTL. That's something I have mentioned already before. But it can also generate a simulation model that you can use as the reference model in your verification framework. And it can also generate a random assembly program generator that will be using the custom instructions so that you have a test stimuli into your verification. Okay, so now to the last part. In the last part, I would like to briefly mention that we have actually very recently announced new products which are enabling exactly what I was talking about. The first product is a 10th generation of our Studio tool. We call it Studio Fusion. And fundamentally, if you have used Studio before, it's still doing the thing that Studio has been doing for 10 years. It generates the software tools as well as the RTL from one processor description. Obviously, we have improved that capability by improving the design language. We now generate more capable software tools, for example, a microarchitecture aware compiler. But another big improvement in Studio is this introduction of these levels of customization. So with this new tool, you can decide whether you want to only configure our processors, whether you want to add new instructions in the bounded customization way, or if you want to design your own completely custom processor from scratch. The second product we have recently announced is our new L110 processor, which is the most area and power efficient processor we have ever introduced. It sits very low in the, let's say, performance range. It's targeting a replacement of FSMs or IoT on the edge devices and similar type of devices. And as a baseline IP, it's extremely competitive. At the same time, it does support the extensive configurability that I was talking about, and it also supports bounded customization. So you can take it completely to next level by adding your own custom instructions into it. And the last slide is a summary of what we believe is the responsible approach to instruction set customization. The first aspect is high quality baseline IP. That means you will not have to start your customization from scratch. You will not have to build the entire processor. And that also means that the baseline processor was verified to very high standards. The second aspect is an easy to use design methodology, which will not require you to be a processor expert in order to customize an existing processor design. The third aspect is that when you customize a processor instruction set, it doesn't mean you have to change just the RTL implementation of the processor, but you need to update all the software tools as well. And if you can use a tool which will automate that process and build all of these things from one description, it will be much more efficient than doing it in the old and traditional way. And the fourth aspect is the verification, which means not just the verification of your customized bits of the processor, but also a clever approach to verification from the IP vendor, which will not expose you to re-verification of the entire processor IP, but will let you focus only on the bits which differentiate your solution. And with that, I will thank you. Thank you for attending this talk, even though it's quite late in the day. And I believe we will have a couple of minutes for questions if you have any. Thank you.
Thank you for your talk. So you said that you needed both the architecture and the microarchitecture. So can you say a bit about what the designer has to specify as the microarchitecture in order to generate the RTL?
Okay, so do you still hear me? No? Okay, good. So the question was, in case you couldn't hear, that I was mentioning that Codal is able to define both the architecture and the microarchitecture of a processor. So what does it exactly mean? So from the perspective of designing a completely new processor in Codal, this means that you have to define the pipeline of the processor, and you also define in Codal, and this is, let's say, the trick that we do and how we combine all of this information in one model. You define architectural aspects of the processor, like the individual instructions or the register files which exist in the processor, which you wouldn't otherwise not do in such, concrete way in other HDLs. So when you're designing a processor from scratch, you have to take both of these approaches. And there are some shortcuts that we can afford in some cases, but To simplify, let's put it that way. However, if you decide to customize our existing processor and you are happy to use the bounded customization approach, the only thing that you have to really define is the semantic of the instruction. So if you remember my slide, and I can go very quickly back, this instruction, for example, is doing the mathematical, expression that's just above the return line. And essentially that's the core of what you need to define. We know that this bit of the instruction will be inserted into the execution stage of the processor. So you don't have to tell this to us. We will be able to do this automatically in Studio. We also knew that we need to extend, for example, the decoder, which is another piece of logic in another stage. But again, this is something that we can completely hide from the user. We know that you want to add another arithmetic instruction, so we need to know what does it semantically do, and that's everything that you need to provide. Obviously, if you decided to do more complex modifications to our processor, then you would have to open up the entire codal model, which will consist both from the description of the architecture, as I mentioned, the instruction set and other resources that are available in the architecture, and the pipeline of the processor, and modify whatever is needed in your use case.
Thank you. Another follow-up is that you said that when you are adding a new custom instruction, the RTL generator takes into consideration that instruction, optimizes the final RTL. The code does that. If I were to add, let's say, 5 or 6 new custom instructions, would it find the global optimized RTL design, or does it do a greedy incremental step-by-step optimization for each instruction added?
I'm not sure what do you mean by the optimization, because what Codal essentially does is that it translates your description in Codal into RTL, right? And the level of abstraction between these two can in some cases be quite high. You can define some things in Codal on higher level of abstraction than it would be in RTL, but in many cases it's very similar. So it really depends on how do you design the instruction. For example, if you want to reuse certain resources between different instructions, then you have to write the Codal code in a way that you isolate that resource into one place where you call it from different instructions, for instance, so that you make sure that you're not creating an optimal design. And then obviously once you go into synthesis with the RTL, you can also rely on the synthesizer to do certain optimizations, but it's in a way out of our control.
Yes, thank you.
Sorry, we're just University of Virginia. If you can give a little bit more details about the new release, or you were very cryptic. So ISA, is it RISC-V?
Yes.
And is it on the level? You said FSM. Is it on the level of an M0 ARM or more?
Yeah. So exactly, the new Core L110 is a RISC-V processor, as all of our processors are. It is RV32 based, and then it has plenty of the standard extensions. I think the ones which are most important to mention is that we do implement all the existing code compression extensions, because that's very important in RISC-V. The code density used to be for a long time a big problem compared to the ARM architecture. And exactly as you said, if you want to compare it to something in the ARM portfolio, we would be on the same tier as Cortex M0 Plus, for instance.